So in this video, we want to begin to talk about the idea of continuity. So hopefully at this point you've looked over the notes, the first 2 pages for the 2.6 notes, as I describe a little bit about what continuity is, the idea of a graph being connected, being able to be drawn without lifting our pencil, kind of the generic definition, and then I gave you some examples of things that can cause it to not be continuous, to have some gap or break in the graph. And so those examples are important to look at because that's going to lead up to what we're now going to talk about, which is the formal definition of continuity. It gives us a way to check to see whether something is continuous. So f is continuous at x equals c if and only if, and there are 3 conditions that need to be met. First is that f of c has to be defined. If the function is undefined, then there's no point on that graph, and so therefore by virtue the graph's going to have a break, whether it's a hole or an asymptote or the graph jumps. There has to be something if the graph is undefined at a point. So that must happen. The second thing is, if it's continuous, in other words, the graph's connected with no breaks and gaps, then the limit as you approach C has to exist. Right? The values around C have to be closing in around the same number. Otherwise, it's not going to be continuous. There's going to be a gap. If they're not closing into the same number from both sides, then there's got to be some kind of a gap there. And last thing is you have to have both of those things being equal. The limit has to be equal to the function value. The limit has to be equal to the function value. And so those things all together are the conditions for a limit. So if you just have the first two, function values defined, limit exists, but they're not the same, then there's got to be a gap in the graph because that function value is popping over somewhere other than where the limit's going. So there would have to be a jump. So they must be equal. And so using these now, we're going to look at some examples checking on continuity. So first, consider the following function here. F of x equals 3x squared plus x plus 12 over x squared plus 3x. And we're asking the question here, is this thing continuous at x equals negative 3? Is this thing continuous at x equals negative 3? So we have 3 things we need to check. So the first question, I just ask them in order, is f of negative 3 defined? Is f of negative 3 defined? Right? Can I plug negative 3 in and do I get a numerical answer? And a quick check tells us, well, no, actually it doesn't. Because if I plug negative 3 in, I'm dividing by 0. So immediately we're done. That example, we don't have to check the other things. I think this one turns out it might actually have a limit. There's probably a good chance it maybe actually has a limit, but it doesn't have a function value. So that's all that matters. Let's consider our next example here. This example here involves a piecewise function. F of x equals x squared minus 1 over x minus 1, where x is not allowed to be 1. Or it's 3 when x is 1. So we go through our checklist. Here we're checking continuity at x equals 1. Because the rest of the places we're not going to have an issue really. But at x equals 1, we need to check here, this crossing point, where it changes. So is it defined? Sure. F of 1 is equal to 3. F of 1 is equal to 3. Does it have a limit? So notice here, since it's equal to that fractional expression anytime x is not equal to 1, that's the only part that's involved in the limit. Because the fact that at x equals 1, the graph is 3, doesn't really matter to the limit, because the limit's only interested in what's happening around 1, not at 1. And so, as we begin to do the limit here, we're just going to look at the limit of that fraction. We quickly find, hey, that limit there involves division by 0. Involves division by 0. So remember, in this kind of a problem, we're going to need to factor. So we factor the numerator. It's a difference of squares. It factors as x plus 1, x minus 1, and then the bottom is already broken down as much as it can be. So we can go ahead now and cancel out that x minus 1, and we can go ahead now and take the limit. And so it does have a limit, and that limit is equal to 2. But here's where our problem comes in this particular one here. The limit and the function value are not the same. And so therefore he also gets disqualified from being continuous.